Okay, so maybe, yeah. So this course, is mathematical methods course, mathematical methods in physics. And actually a lot of this material you probably already have seen. You have already done in your university courses. But so some of the material will be known to you, but it will be like refreshing your memory, right? Refreshing the thing. And some other material will be new. Right? Okay, second thing, I think there are two of you are francophones, right? So I will try to speak slowly. However, I have a tendency to start speaking faster and faster as I go on. So if that happens, stop me, okay? To slow down. Okay. Fine. So there are basically 4 topics I'll be covering, right? The first one is linear algebra. Okay, that's the first chapter. I think it will probably take about 7, 8 lectures maybe. The next one will be complex analysis. Third one will be function spaces. For orthogonal, okay, there are lots of topics here, but in particular Fourier transforms. And finally, the last chapter would be differential equations. Okay. So these are the 4 main topics. Each of them will probably require about 8 lectures to 10 lectures. So I'm assuming that it will be about 35 to 40 lectures altogether in this class. But we'll see how it proceeds. And please ask questions. Even if I need to take more lectures, it doesn't matter. More important thing is that you understand everything, right? So just stop me if you have any doubt, ask questions. Okay. The book I'll be following is the book by Denery. And now this is difficult to spell, to pronounce. Krishviki. Okay. Anyway, we'll provide lecture notes. I think the first lecture notes you should get maybe today afternoon or tomorrow. Okay. That'll cover the first chapter, linear algebra. Okay. But in any case, there are a couple of copies, I think, in the library. So if you want to consult the book for anything, you can consult in the library. I won't be covering the entire book because that book really has a lot of material, and if I want to cover that, it will be a 2-semester course. Okay. So what I will do is I will just take selected topics from there, which are, I think, more useful for you. Also, I will not go through the proofs of many theorems. Okay. I'll just state the theorems, try to give you some examples why that theorem is true, right? And more important is how you can use the theorem to solve some physics problems. Okay. So the emphasis will be more on application of the various theorems to help you to solve physics problems. Okay. There'll be tutorials once a week. And in the tutorials, you'll get a lot of experience in solving actually problems. Using this, whatever I'm going to teach you, how to use that to solve concrete problems. Okay? So that will be the tutorials. Okay? I won't be doing too much of that. I'll be mainly giving some examples to show to you that those theorems are sensible or make sense. No? Okay. So also, I think that tomorrow's tutorial, the tutor will give you a problem sheet. That problem sheet is for us to know how much you know, right? So that then we can design the course accordingly. Okay, so that's the purpose of that, the first sheet. Okay, any questions on this up to now? Are you all familiar with the matrices and the determinants of matrices and so on? I will need that in the first chapter. In any case, I will go through it once I arrive there. But I just want to know if you are familiar with it or not. In any case, I will refresh the memory, right? Okay. So now let's start with the first chapter. So the first notion is that of vector spaces. vector spaces. Okay. Now, you are all familiar with the vectors, right? So, consider, for example, two-dimensional space. Two-dimensional space, this is my two-dimensional space, the blackboard is two-dimensional plane, right? Now, here you can, the vectors are this, for example, this is a vector, right? This is another vector, right? These are all vectors. So, vectors have what? Vectors have a direction and the length, right? So, in this two-dimensional case, you have, I'm just showing you some vectors here. Now, this vector, you can, suppose I choose the two axes here, x and y axis. These are my two axes in this two-dimensional space. Then I can define this vector by giving it the coordinates, right? You draw a perpendicular to the x-axis. Then this is the coordinate x, and that is the coordinate y of that point. So, this will be some point. Let's say this length is x1, that length is y1. Then this point is the same as x1, y1, right? Similarly, if you take this vector, again do the same thing. Draw a perpendicular here. Then this length will be x2. So, this will be some x2, y2, where x2 is this length and y2 is that length. Right? So, a vector in two dimensions can be completely defined by specifying these two coordinates, right? X and y coordinates. So, these are the examples of vectors. But what is the most important property of these vectors, or at least one of the very important properties of the vectors? That the thing is that you have a notion, you can add these vectors, right? When you add these vectors, you will get what? Again, another vector, right? And what is the rule to add these vectors? It is simply to take these two vectors and draw a parallelogram, right? Draw a parallelogram. So, this line is parallel to that line, and this line is parallel to that line. So, this is a parallelogram, and take this diagonal. That is the sum of these two vectors, right? So, if I call this vector, let's say v1, and this vector is v2, let's say v2, and this is v1, then this vector is v1 plus v2. I think this, you're all familiar with this, the rule of addition of vectors. Well, if I do that, you can ask, for example, what is the coordinates, what is the coordinates of this point? Well, if you draw a perpendicular down here, this length clearly will be equal to that length plus that length, right? So, this length will be x1 plus x2, and similarly, this length will be the sum of this length plus that length, right? That's easy to see because you draw a perpendicular here, a perpendicular like that, then this whole length is equal to that length plus that length, but that length is the same as that length, right? So this one is y1 plus y2. So, in other words, the vector v1 plus v2 has the coordinates x1 plus x2, comma y1 plus y2. Okay? This is the rule of addition of vectors in two dimensions. You can, of course, generalize immediately to any dimensions. For example, in three dimension. In three dimension, you will have one more axis, say z axis, right? And every vector you can define by finding its projections on the x, y, and z axis. So, then a vector will be specified by specifying the three coordinates x1, y1, z1, and so on. And then when you add the two vectors, it will be again summing up, adding up the components. These are called the components of the vectors, right? This is the component of the vectors, of the vector v1, x1 and y1 are the components. Similarly, of vector v2, x2 and y2 are the components. Then the sum of the two vectors, v1 plus v2, its components are x1 plus x2 and y1 plus y2. Okay. So, this is one notion. So, what is the important point here? That the set of all vectors, okay, this is a set. I mean, if you consider all the possible vectors in two dimension, that will form a set. Okay. But what is important about this set is that there is a rule of addition. You see, you have a rule here. You have to specify a rule which tells you if you take these two vectors, add them up, you will get another vector in the same set. Okay. So, this is the important point. So, the first important point is that there is a rule of addition. Okay. So, when you add the two vectors, you get again an element of the same set, not something outside, the same set. right? The set of all the vectors. So it's again another vector. That's one thing. Second point is that there is also a notion of multiplying by a number, right? So if I take a vector here, and if I ask you what is 2 times that vector, well, it's nothing. This direction is the same, but just the length becomes twice, right? So you know also another concept, another let's say notion, and that is multiplication by a number. So if you give me a vector, I can multiply by any number, say let's say 2, then I will get another vector again, which will be whose direction will be the same, but length will become twice the original length, right? So there is a notion of multiplication. So the second is that you can multiply by numbers. These are the two important notions. So when you multiply, say, a vector v by multiply a vector v by x, so x times v, or not, let me not call x, say a times v, where a is a number, right? A times v will have the same direction as v. The direction will be the same, except that its length will become a times the original length. Okay, that's what we are familiar with that. So these are the two important points. But now you can, so now what we are going to, okay, we also can say a few more properties. So let's suppose I have v1 and v2, two vectors. Well, I can multiply an a with v1, some number a with v1, it will be again another vector. I can multiply some number b with v2, that will be again another vector, right? So this vector is nothing else but you just multiply the length of the v1 by a, okay, but direction is the same. Similarly, this will be b times the length of the v2, but direction being the same as v2. And then I can also add these two vectors, right? Again, by doing the same rule of adding the two vectors, this will again be a vector. This will be again another vector. Yeah. So these are the two very, very important features that the vectors satisfy. Okay. A third thing is that there is a notion of zero vector, right? There is something called the zero vector or null vector. A null vector, okay? Null vector, I don't know how, let's see if there is a way to, yeah, okay. I don't know. I will just use, at the moment I'm using the arrow symbol. So I will just write it like this, 0 with the arrow there. What is that vector? That vector is nothing else but this point itself, right? So its components are simply 0, 0. If you take the x and y components of this vector, it is 0, 0. What is the special property of this vector? The special property of this vector is that if I take any vector v and add to that the 0 vector, what am I going to get? Get back the vector v itself, right? So I will get back vector v. So this is the definition of the 0 vector. The 0 vector is the vector such that when you add it to any vector, you get back that same vector, right? That's the definition of the 0 vector. And of course, also it satisfies another property. If I take any number a and multiply to 0 vector, I will again get 0 vector. That's clear, right? I mean, because after all, this 0, 0 point, right? When you multiply by a, just changing the length, but the length is 0 anyway to begin with. So it's a 0 vector. So these are the main things. So now, so what I did was just, I'm trying to abstract. I mean, you are familiar with these two-dimensional vectors and how you add, and you are familiar with all that, no? So what I'm trying to do is to extract from that the abstract concepts, right? And then we define the vector space using the abstract concepts. What is the purpose of that? The purpose is that now, once you have these abstract definitions, you can extend way beyond this two-dimensional example, you know? You can go even to infinite dimensional spaces, right? But the point is that you need to have precise definitions, okay? But those definitions will be motivated from the experience you have already, okay? So from that we'll abstract, okay? So this is a general way the mathematics proceeds. I mean, many times the mathematics, the way it develops is you have some simple examples, right? You abstract from that the general ideas, right? And then you postulate those general ideas so that then you can apply it to much more general cases. So this is the way it proceeds. Okay, so we will now just formalize these things, abstract from this the main ideas, and I will make the precise definition of the vector space. Okay. So first of all, so vector space is a set. And I will try to use the same notation that is used in the notes so that it will be easier. I will call this set S, the set S of elements, right? And I will always, instead of using this, this notation with the arrow, I will use the notation Bra and Ket notation, which will be used in quantum mechanics. Okay. So I will use this S consists of vectors v, w, etc. Right? There will be infinite number of elements here, but so notation for the vectors will be this bracket notations. That is because you will be using that in quantum mechanics course for that reason. Okay. So yeah, sorry. There was a question? No. Okay. So first thing is that there is a notion of addition. Okay, so I will use the same thing. So if let's say A and B belong to S, if A and B belong to S, then A plus B also belongs to S. So this is just saying that there is a notion of addition. I have defined an operation inside this set called addition, which gives for every two pair of vectors, it gives you a third vector, right? There's a rule, there's a notion of addition. This was just an example, what I described before. That's one thing. So in order to, of course, so you have to define this. So it's not just this set. On top of this set, you have a notion of addition and multiplication by numbers. So that you have to put in by extra outside information. Okay. The second point, so this is the, okay, there are lots of points here, so let me just write it like in the same way as they're written in the notes here. If A belongs to S, and let's say alpha is some number, now this number could be real or complex, okay? If you only allow real numbers, then you say that that vector space is a real vector space. But if you allow also complex numbers, then you say that's a complex vector space. I will always be working with the complex numbers. The reason again is in quantum mechanics, the states of the Hilbert space or the wave functions, they will be complex. Okay, it will be complex vector space. So I will be using complex numbers. But if you just specialize it to the real numbers, it becomes real vector space. In the example I described before, it was real numbers. So there was a real vector space. But I will be more general than that. So I will allow this alpha is a complex number. Is a complex number. Then there is a notion of multiplication. You can multiply this number with this vector, and that will give you again another vector. Okay. So then alpha A also belongs to S. Okay. So we have these two definitions, right? The set, the rule of addition, and the rule of multiplication by complex numbers. So this you have to specify. Okay. Then the third one, C, that there is a null vector, that there exists a null vector. And now I will, since I'm using this notation, I will denote this by 0. This will be the null vector. The property of that is that, so such that, I mean, this is a definition of that. For any vector A, you add 0, you get again A. That's the definition. And finally, there is a notion also of inverse. You see, whenever there is an operation you have given, you can ask the question: is there an inverse of that operation, right? So in what sense inverse? So I'll just write. So if A belongs to S, then there exists a vector A prime such that A plus A prime is equal to the null vector. Okay. This is very clear. Again, going back to the two-dimensional example we were discussing, if suppose this was my vector V, then what is the inverse vector? I mean, I just use the word inverse, but you don't have to. What is the vector? What is the vector such that when you add to this vector, you get the null vector? Answer is simply you just take the same line, I mean same direction, but same line but in the opposite direction with the same length, right? So when you add this vector to that, so this is my V prime. Okay, when you add these two vectors, when you add them up, it will just give you 0 vector, right? So this indeed in this example it exists. Now what we are saying is this is a general definition now of the vector space. So there must be, let's say, the negative of that vector in some sense. After all, what is V prime? If you look at the V prime is nothing else but minus V, right? You take the components of V and multiply by minus each of the components, you get V prime. Right? So this is the thing. I mean, okay. So here, okay, that's main points here. Okay, now we have to say something more about, okay, here is my rule of addition, rule of multiplication. But I mean, we of course in the specific example we know precisely what we mean by that. But now we are trying to abstract, trying to make it general, right? So we need to specify a little bit more about what this addition should satisfy, what this multiplication should satisfy. Okay, so we need to say a bit more. And now unfortunately I have to erase all this. Okay. I mean, do you have any questions? Maybe I should pause before proceeding further, before erasing this blackboard. Do you have any questions on that? Feel free to ask questions. Yeah.
About the notation, if the notation have some linear, just
yeah. No, it's because okay. It's simply because in quantum mechanics you will have the state, but you say a state of a system, right? A state of a system is usually denoted in this way. I mean, I don't know, something like that. Huh? Okay, this is the bracket notation. So this is a particular state of the system, quantum state of the system. But what is the important point about this thing is that you have a notion of superposition of states. That superposition of states is the notion of addition. So if I have a psi and a psi prime, then I can superpose these states, right? And that is where the addition comes. Right? So in fact, in quantum mechanics, the Hilbert, the set of states is a vector space on which various operators will act, like Hamiltonian operator or various other operators will act. So just because of you'll be I think the very next lecture in the afternoon, you'll be studying quantum mechanics. I'm using this notation, and also because in this book, this notation is used, so not to confuse you with using many different notations. Yeah, yeah, that's a very important point. And in quantum mechanics, the Hilbert space of states is a vector space, and there is a notion of addition. That's why you get all sorts of interference patterns and everything, because you have superposition of states. Okay, so now let's see. So far we have defined these things, but these, I mean, they must satisfy some conditions. So the next set of things will be the conditions on this addition and multiplication, what they should satisfy. Okay. So first of all, again, so let me again go with the same in the same sequence. So now suppose I have let's say 3 vectors A, B, and C. They all belong to S. So the first property you see is that if I take A plus B, okay, this will be some vector in S. But this is the same as taking B plus A. Again, pretty obvious from your two-dimensional example, right? It doesn't matter the sequence in which you add is the same. Right? This rule of drawing a parallelogram and taking the diagonal, it doesn't matter which way you take the first vector, is the same, right? So this is called commutative. Commutative. Okay, this is a commutative rule, meaning the order doesn't change. It doesn't make any difference. Right? That's one thing. Second thing is now I have 3 vectors here. I can say I first add, let's say, A and B. This will be some vector. Now to that I add the C. Again, this will be some vector. Right? This is the same as first adding B and C. This will be some vector, and then add A to that. The two results are the same. This is associative. Once again, this is again obvious in the two-dimensional example, right? But now, now we are not talking about a specific example, right? See, the whole purpose here is to make it general, right? Not a specific example, but general. But we want to extract all the features from the example, all the important features from that example, right? So important features were, first of all, the definitions, addition and multiplication, and then addition satisfies this condition, right? So we use that. This is associativity. Associative. Okay. Then, okay, we have defined this 0 vector, right? But there's also, since I'm talking about a complex number, this alphas, I erase that. The numbers that I'm multiplying with, alpha, etc., to the vector A, that is a complex number. Now, in the set of complex numbers, there is a very important number, which is 1, right? What is the property of 1? 1 multiplied by any number is again the same number, right? That's the identity, 1, unit number. So 1 times A, so 1 is the special complex number, is again A, okay, which is again true for you're multiplying a vector by 1, you're not changing anything, right? Its length is the same as original length, direction is the same. Okay. So this is as far as the multiplication is concerned. But now we have to specify a little bit more about the multiplication rules. So once again, let's say this is, I call this before I had used the capital A index, right? Capital A. But the capital A was mainly the definition, I mean the statement that under addition and multiplication the set is closed, right? I mean you get back the element of the set and the notion of the null vector. But now what we are doing is the properties of that two operations, right? So that's why it's a different, and again here we have different here. Then another thing, you can ask the question, suppose I have two numbers, alpha and beta. Suppose I first multiply by beta, which is some vector, then I multiply by alpha to the resulting vector. What is it? Is there some, so I take alpha, beta, two complex numbers. And A is a vector. Then beta times A is of course is a vector, whatever rules I have given for the multiplication. Then to this vector I multiply alpha. Okay, this will be again another vector, right? The statement here is that this must satisfy the property that this is the same as alpha times beta, which is a complex number, product of two complex numbers, multiplied to A. I mean, they all look very trivial, right? I mean, in the sense that in two-dimensional example, it's all obvious, right? You multiply first by a number 2, then you multiply a number 3. the result is the same as multiplying by number 6, right? Is that okay? Then so this is what is called this again. You see this like associative law. You see what is in the associative law? What is happening? I have three terms, three objects, and then I put a bracket in the one case like that. In another case, I put the bracket like that. That's exactly what we are doing. You see, I have three objects, alpha, beta, and a. Here I put the bracket here in the second and third guys. Here I put the bracket between the first and second guy. So this is again associative law. Associative. So this was the associative law for the addition. Law for addition. And this is the associative law for multiplication. For multiplication. Okay. That's that. And then a few more properties it satisfies. For example, in the complex numbers, you have the notion of addition, right? The sum of two complex numbers or sum of two real numbers is again a complex or a real number, right? Adding two numbers, 2 plus 3 is 5, no? Like that. So if I take this sum of the two numbers and multiply to the vector A, that is the same as multiplying alpha with A and adding to that beta times A. Yeah, that's again going back to the two-dimensional example. Suppose alpha was 2 and beta was 3. So what we are saying is 2 times A plus 3 times A. You add them up. That is just going to give me 2 plus 3, which is 5 times A, right? That's so this law is called distributive law. Distributive law with respect to addition of numbers, complex numbers. Okay. Instead of writing the whole thing with respect to, WRT, with respect to addition of complex numbers. And finally, you can also ask there is a distributive law. You can say alpha times, say, vector A plus B is the same as alpha A plus beta B. Okay. So this is the distributive law with respect to addition of vectors. See, here you added the complex numbers, and there's a distributive law with respect to addition of complex numbers. Here I'm adding the vectors. So distributive law with respect to addition of vectors. Okay. So these are all the conditions. Okay. So once again, so most important point was that in this set we have a notion of addition of two elements and gives you another element. So there's a rule. You have to specify the rule how you're going to add, right? That's okay. Second thing is that there's a notion of multiplication by numbers, could be a real number or a complex number, right? I will be mostly working with complex numbers. Whenever I want to specialize to real numbers, I will say specifically that I will restrict myself to real numbers, but generally it will be complex. Okay. Then there exists a null vector, right, and the inverse vector. I mean, for a vector, its inverse vector exists. Then those two operations, multiplication and addition, satisfy these properties. Okay. This defines a vector space. Okay. If you can find such operations, multiplication and addition, which satisfy these properties, then that is a vector space. Okay. As we saw, all these conditions look pretty trivial. I mean, pretty obvious for the known thing, like two-dimensional vector space, three-dimensional vector space. This is obvious. These are conditions satisfied. Okay. So now let me give some examples. Yeah, I think I can consider some. Any questions on this? On these conditions? Yeah.
Did you define a vector space?
Yeah, this is the definition of vector space. I said S is a set of elements, right? But in this set, I have two operations defined. One is the addition, and other is the multiplication by complex numbers. But those rules that you have given must satisfy these conditions. Okay, and on top of it, there must be a null vector. Okay, and the inverse vector. Inverse in the you know what I mean. If a vector A exists, then some vector A prime exists, such that the sum of the two gives you the null vector, right? So, yeah.
In the last statement here, you've written alpha multiplied by A plus B. Then in the answer you've written.
Oh, sorry. I wrote it wrong. This is alpha. Yeah, correct. Alpha. Thank you. Yeah.
So if you are to define a vector space, you will say it is a set of elements, the set of elements which must satisfy this condition.
Yes.
Now you have to state the conditions in the definition of the vector space.
Yes. So I mean, so the vector space comes with the set together with two operations, addition and multiplication. Not arbitrary rules. I mean, they meaning that you have to specify two rules: a rule of addition, rule of multiplication. But those rules are not arbitrary. I mean, they have to satisfy these conditions, right? And also there must be null vector, right? There must be null vector and the inverse vector. Yeah, those are the main conditions. Maybe I shouldn't use the word inverse, because inverse could be misleading. Probably that's not. You see, inverse by that, suppose I give you number 2. What is the inverse of 2? Is 1/2, right? So inverse is usually used in the sense of multiplication, right? But here I'm using so you see, in the usual thing that you say, 2 inverse of 2, which you denote like this, 2 to the minus 1, that is 1/2, right? So what is the property here? 2 times the inverse, which is 1/2, is 1, right? So this is the inverse with respect to multiplication, right? See, in multiplication, what happens? 1 times anything is the same thing, right? So 1 is a very special element, 1. Similarly, when you talk about addition, 0 is a very special number, because 0 plus something is again the same thing. So when you talk about the inverse with respect to addition, not with respect to multiplication, then if I give you 2, what is the inverse of 2 with respect to addition? Is -2, because 2 minus 2. So in this sense, I'm using the word inverse, but please don't confuse it with this notion. I mean, so maybe I shouldn't use the word inverse. I just mean, if I give you a vector A, there exists another vector A prime, such that A plus A prime is null vector. Okay. So please disregard this inverse, because inverse could be confusing. Yeah.
The trivial definition of a vector is a vector has magnitude and direction, right? And now we have a 0 or null vector with magnitude 0.
Yes.
And what is the direction for?
There's no. I mean, it has no direction. Yeah. You're right. Yeah. Correct. Okay. This in the question of magnitude and thing. At the moment, you see in these definitions. So now this is an abstract definition. Here I have no idea what is the length of a vector. You see, I don't know. I have not defined what is the length of the vector, right? I mean, I started with something which you already know, 2-dimensional vector space. There I know what is the length, right? Okay. But now in this, here I have no idea what is the length of this vector space. I mean, those vectors. In fact, I have to define. I will come to that later. Maybe not today, tomorrow, or next lecture I will come to the definition of length for abstract vector spaces, and what conditions the length must satisfy. Okay, but at the moment, so far you see the only thing that we know here is the addition structure of addition. I mean the how you can add the two vectors and multiplying a vector by a number. But I have no idea what's the length of this vector, right? Or scalar products. You see, in 2-dimensional vector space, I can talk about, if I give you 2 vectors, I can talk about the scalar product of these 2 vectors, which is the length of this vector times the length of that vector times cosine of the angle between the two, right? Here I have not defined what is scalar product, right? I will come to that in the next lecture. Okay. So let me give you some examples. Some examples which are pretty straightforward, and some examples probably which are not so straightforward. Okay, so one example is so one example we already discussed. So I will not explain again. Example is any two-dimensional plane Okay, I mean two-dimensional vectors with the rule of addition and multiplication as I had defined already, right? So that was the example. Another example is say a set of matrices, say n cross m matrices. So you know what is the n cross m matrix? It's a matrix. It has n rows and m columns. So you have, I don't know, there are n rows here. So let's say some matrix A, which has elements A11, A12, all the way up to A1m. So there are m columns here, you see, and A21, A22, A2m, and finally all the way up to AN1, ANM. So n rows and m columns. If you consider the set of all n cross m matrices, and okay, so that is a set, but now I have to define what I mean by multiplication and addition, right? So I will define, if I take some number alpha, and alpha times A is by definition, you simply just multiply each component by alpha, okay? So this will be a matrix again, alpha A11, alpha A12, alpha A1m, and similarly all the way up to alpha AN1, alpha ANM. So this is the rule of multiplication. Okay. Now, what is the rule of addition? So the rule of addition is if I give you two matrices A and B. So A is this, A is that already, and let's say another matrix B, which is B11 up to B1n, and Bn1 to Bnm. So I'm given two matrices. Then I want to define what do I mean by A plus B. I have to define that. Well, it is simply just take these components here and add them up, right? So this is A11. First element is A11 plus B11. Second one is A12 plus B12, all the way up to A1m plus B1m. You know, just add them up, term by term. AN1 plus BN1, all the way up to ANN plus BNM. Okay, so this is the rule of addition. So you see, again, important point is that not only the set, you have to define what you mean by addition and multiplication. Here I've given the definition. Now the main thing is to check if all the properties are satisfied. Okay. So first of all, what is the null vector? Null vector is simply the vector with all the entries 0, right? Because obviously when you add that zero matrix to any matrix, I will get back the original matrix, right? So that is the null. What is the inverse? You simply just take the minus, right? So that's, I mean, if A is a matrix given, A prime matrix such that A plus A prime is 0, A prime is simply obtained by A by taking minuses, multiplying by minus everywhere, right? That's, actually that is a general rule, right? I mean, after all, I mean, that's a general thing. In general, even if you look at the original abstract definition, you had vector A, let's say, then what is A prime such that A plus A prime equal to 0? Well, A prime is by definition, well, I mean, it's immediate, is simply minus 1 times A, right? Because, let's see if this is true. Well, let's take A plus minus 1 times A, okay? So this is 1 times A and that's minus 1 times A. Now use the distributive law, right? That's the same as 1 plus minus 1 whole thing times A. I just use the distributive law, right? But 1 plus minus 1 is 0, so this is simply 0 times A. That's 0. So it's always that. I mean, the inverse is nothing else but multiplying by minus 1 the original vector. Okay. Then you can prove that all the conditions satisfied. I mean, this rule of addition is obviously commutative, right? It's also associative. I mean, it's all the things you can check immediately. So please do check it. I mean, to check if all the conditions are satisfied or not. So this is one example. Another slightly more complicated example, well, not more complicated, is an example of infinite dimensional space. So let's say, so I take another example now. So the set of, say, all functions, or even let's make it periodic functions, periodic and periodic functions. F of theta, where theta is between 0 and 2 pi. Okay, this is just an example. Periodic functions. Consider the set of all periodic functions. Okay. Now this is a set. Now I have to define what do I mean by multiplication and addition. Right. So multiplication is immediate. You take any number. So this could be real or complex. So let me consider complex functions. So complex functions. So all periodic complex functions. This could be real also. I mean, if you could make it real, that doesn't matter. Complex functions. And then a multiplication by a complex number alpha, if alpha is a complex number, okay, then multiplication is simply alpha f theta is nothing else but you take f, evaluate it at theta, and this will be some number, complex number, and multiply this complex number by alpha. Right? So pictorially, if I draw a plot, so here is theta and here is, say, f theta. So this will be something, I don't know, let's say periodic function, so it could be something like that, 0 to 2 pi. Okay, the periodic function. Periodic means that the value of f at 2 pi is the same as value of f at 0, periodic function. Now if I multiply by, say, 2, let's say I want to multiply by 2 this function, then what do? I multiply at each value theta. At this value of theta, it will be some, f of theta will be something. You multiply that by 2. Okay, so this multiply by 2 is that, right? If you take this point here, you multiply this by 2, it will be like this. So and then you plot it. This will be again another function, right? Periodic function again, correct? This function is by definition 2 times this original function. So that tells me, that gives you what is a definition of multiplication, right? It's what is called point-wise multiplication. At each point, you see what is the value of the function. That will be some number. You multiply that number by the alpha. Alpha is whatever number you are given with. The result will be again another function. Okay, the resulting function is by definition, you say it's that alpha times the original function, right? So this way I have defined what I mean by multiplication, right? Similarly, addition is also point-wise. If I give you 2 functions f and g, if I give you 2 functions f and g, these are 2 functions, 2 periodic functions, then what do I mean by f plus g? So I want to say what is f plus g evaluated at some theta, right? Precisely. Good. Yeah. So that's again point-wise addition. F of theta, g of theta. You see, this is a complex number. That's a complex number. The sum of these two is again a complex number. And what I'm saying is that f plus g is a function such that when you evaluate that function at theta, that is the same as this number plus that number. And that should be true for every theta, for all theta. Okay. So pictorially again, if I draw, let's say 0 to 2 pi, say function f is something like that, and this is function f, and say this is function, maybe function g could be even something like, so this is g. Okay. Then what I do, the f plus g is simply the function such that at each point you look at the value of f and the value of g and then add them up. So this plus that, it will be something here, right? And you do that at each point. Okay. whatever the result you will get, you join them all. I don't know, it must be some complicated, I'm not going to draw that thing, but whatever you get, that will be the f plus g. Okay? So this is so this way I have defined what do I mean by addition. Right? Now you can verify that these two rules satisfy all the conditions. The condition of commutativity is clear. G plus f is the same as f plus g, right? Because it's defined, I mean, this rule is commutative. So therefore, associativity is also clear. I mean, you can just check that all the conditions that they have to satisfy is satisfied. Distributive law, all this is satisfied. And what is a null vector? Null vector, the null function is simply zero function. Okay? So null function, I don't know, how shall I write it? The null function evaluated at theta for any theta is simply 0. So the null function is just that, just this. Its value is 0 throughout, 0 to 2 pi. So it's clear that when I add to any function, since the function is the rule of addition is this. Here I'm saying the null function evaluated at any theta is 0. So you see that you get back the original function. Right? This satisfies the condition of null. Is that maybe was I too fast the last? I mean, what I'm saying is that let's use let's check if this is null function or not. So I want to see if I take a function f and add to that the null function. Okay. Now the rule of addition was that if I evaluate this, the result of this function, I mean this function on theta, that is the same as f of theta plus null function evaluated at theta. But this by definition is 0, right? So this is the same as f of theta. So since this is true for all theta, that means f plus null function is the same as f, right? Which was the basic property of the null. That's a null function, null vector. And similarly, the inverse of f is simply minus f, right? If I take f is something here, then this is f, then the inverse of f is simply multiplied by minus. So when you add them up, you will get the 0 function. Okay, so that's this is infinite dimensional. You see, this is infinite dimensional because periodic functions you can always expand in the Fourier series, right? But there are infinite number of terms in the Fourier series. So to specify the function, you need to specify infinite number of Fourier coefficients, right? I mean, this we will discuss in much more detail in the third chapter. Okay, but you already know. So you have already seen Fourier series, right? So I'm just using that to explain why this infinite dimensional space. You see, in the example of 2 dimensions or 3-dimensional vectors, I mean, what do I mean by dimension? I will come to the precise definition of dimension soon. Maybe today itself I will come to that. But you already have a notion of intuitive idea of what is a dimension, right? So in two-dimensional case, what we had, this was a vector, right? Now, to specify this vector, all I need to specify is the 2 components, right? So a vector is completely specified by giving 2 informations. Its x component and the y component, right? So that is a dimension. The dimension is the same as the number of independent informations you need to give to specify the vector, right? So in this case, I just needed to specify 2 numbers, x and y. And I could write the vector as xy, right? So 2 information I need here. Right? Now let's go to this space, this last example, where I'm looking at the function space. Well, a periodic function I can expand in terms of Fourier basis. So let's say fn e to the I n theta, summed over n, going from minus infinity to plus infinity, right? Okay, this is a bit not very precise. I mean, we'll make it more precise when we come to the third chapter, because there are all these issues of whether this series converges. There are what kinds of functions you can expand. There are subtle issues, but let's ignore those subtle issues. But you know that there will be some an arbitrary, a continuous function, etc., can be expanded in this way. Okay. But now, how much information I need to give? I need to specify all these fn's for all this n from minus infinity to plus infinity. So I need to give infinite number of informations to specify the function, right? So that's why it's infinite dimensional. Okay. In quantum mechanics, the states will be a wave function. If wave function will depend on all your positions x. If you are in 3 dimensions, x, y, z. So wave function will be a function of x, y, and z, right? This will be functions. So there will be infinite dimensional, because functions are always infinite dimensional. To specify a function, you need to specify infinite number of informations, right? So yeah, in quantum mechanics, the vector spaces that you will encounter will be infinite dimensional. Okay, let's see, is there anything else I want to specify? To give an example. Okay. So let me move on to now, since I already talked about dimension, let me make a precise definition of the dimension. 230, yeah. Okay. But let's say any question on the function space? You see, unlike here in this example, you know exactly what do you mean by a scalar product, right? Or the length of this vector. In this example, it's not clear. I mean, you have to, there's not at all clear what is the length, even how you define the scalar product of two functions, right? But this will come to later in the, not in this chapter, but third chapter, I think we'll come to that. I mean, I think you've already done quantum mechanics course, right, in the universities, right? But in quantum mechanics course, you know how you define the scalar product of two wave functions. You just take the product of of one guy with the complex conjugate of the other and integrate, right? So that's a scalar product. But so it's much more complicated than that. That's what I'm saying. Okay. So now let's come to the definition of dimension. Again, let's go back to this example here, right? So if I take, let's say, in 2 dimensions, so example of 2 dimension. 2 dimension. So let me draw it bigger. Say this vector I take, another vector I take here, and say another vector I take here. Okay, here is my. Okay. So let's say this guy is x1, y1. This is x2. Actually, let me simplify this a bit. Let me try to simplify this a bit. I take the 3 vectors in this way. I take one vector as that, one vector as that. So this vector is 1, 0. Okay, its length is 1 along the x-axis. This vector is 0, 1 along the y-axis. And this vector is some arbitrary vector with the components x1 and y1. Now, you see, these 3 vectors are not independent of each other, right? Because after all, this vector, so let me call this vector as v1, v2, and v3. So what I'm trying to say is that they are not linearly independent in the sense that I can express v3 as a sum of these 2 vectors, linear combination of these 2 vectors, right? In fact, you can see immediately that v3 is nothing else but x1 times v2. Let me use this 1 here, and that's 2. Okay. X1 times v1 plus y1 times v2. Correct? Because you see, this is nothing else. This is what? This is x1 multiplied with 1, 0. But you remember, multiplication rule was multiplying this to each component. So this is same as x1, 0. You multiply x1 with that x1, and that is 0. And here, that simply gives me 0 and y1, because y1 times 1 is y1. You add them up, that is simply x1, y1. Right? So this is true. I mean, v3 is indeed sum of linear combination of these 2. Some number times v1 plus another number times v2. Right? So when such a thing happens, then you say that these three vectors are not linearly independent of each other. Okay? So when this happens, you say V1, V2 and V3 are not linearly independent. Linearly independent. So that's the definition of linear independence. I mean, this is an example of thing. So, to say, on the other hand, if I take another example where I just take V1 and V2, not V3. I don't include V3. Just take these two vectors, V1 and V2. Okay, these two, there is no way you can, you cannot. They are not. They are linear. These are linearly independent. Linearly independent. Right? Because you cannot. Because why is it linearly independent? Because if I consider an equation x times V1. Let me not put it, alpha times V1 plus beta times V2 equal to the null vector, try to see if there is a solution to this equation. Okay? So I have this, I look at this equation where alpha and beta are unknown. Okay? I want to solve for alpha and beta from this equation. And then the statement is that the only solution to this equation is alpha, so consider this equation. Let's work it out. So what is V1 is 1, 0. So this is alpha 0. Okay. This is 0 beta. Okay. Beta multiplied by V2. That's that. And what is null vector is 0, 0. Right. Now the sum of these two, again add the components. So you get here alpha beta equal to 0, 0. This implies alpha equal to 0 and beta equal to 0. Correct. So the only solution to this equation is alpha and beta both are 0. When such thing happens, when this happens, then you say V1 and V2 are linearly independent. Okay. In fact, in this, let's consider, I mean, V1 and V2 may look very simple. I mean, but consider what about V1 and V3? Let's take V1 and V3. Are they linearly independent or not? Okay. So again, let's look at this equation, alpha V1 plus beta V3 equal to 0, null vector. Let's consider this equation and see, is there any non-trivial solution? Is there any non-zero solutions for alpha and beta? Okay. So this guy is nothing else but alpha 0, and that is beta x1 plus, comma beta y1. Right? This V3 is that. That's the left hand side. Let's add them up. So you get here alpha plus beta x1 comma beta y1. That's equal to null vector, which has component 0, 0. Okay. Now I want to solve for alpha and beta. I'm assuming that, of course, here you see the V3 is not parallel to V1, so y1 is not 0. Right? I mean, this is not along. So y1 is certainly not 0 here. Y1 is not 0. And actually in this picture even x1 is not 0. Because it has non-zero components both here. Right? Okay. Now look at this. This implies that this must be 0 and that must be 0 separately. Right? Now if you look at beta times y1 is 0, and since I know y1 is not 0, the only possibility is beta must be 0. Right? So beta must be 0. But if beta is 0, this term drops out and you get alpha equal to 0. Right? So again, this implies that both alpha equal to 0 and beta equal to 0, both. So these are linearly independent. On the other hand, when I added this, when I consider all the three vectors together, you see they satisfy this condition. So I can, for example, take this on the other side. Okay, so you get here this minus V3. See, this is null vector, right? So now you see I have a solution. If I consider some alpha times V1 plus beta times V2 plus gamma times V3 equal to null vector, if I want to solve for that equation, I find there is a non-zero solution. I mean, Consider this equation: alpha v1 plus beta v2 plus gamma v3. Gamma is again another number, equal to null vector. I want to solve for this equation. Okay, I want to see if there exists any alpha, beta, gamma, which are non-trivial, which means not all 0, such that this is true. And indeed, from here you see that I can choose alpha equal to x1, beta equal to y1, and gamma equal to -1. See, that's a solution to this equation, right? I mean, you can just plug it. Alpha equal to x1, beta equal to y1, and gamma equal to -1. You see that this is 0. The sum is null vector. Okay? So this is an example where what it means, the v1, v2, v3 together, they are not linearly independent. Okay? Or they are not linearly independent is the same as the statement that they are linearly dependent. Okay? So they are linearly dependent on each other, which means that one of them can be expressed in terms of combination of others. You can actually try and verify that the moment you have more than 2 vectors, that set will always be linearly dependent. In this example, through two-dimensional plane, if you consider a set of more than 2 vectors, say here was 3 vectors, right? If you take 4 vectors or 5 vectors, whatever, then that set will be always linearly dependent. So that gives you a hint of what is the definition of the dimension, right? Abstract definition of dimension. The abstract definition of dimension is the number of elements in the maximal number of elements which form a linearly independent set, linearly independent set. So that is a dimension. So now you see that can be this can be generalized to a completely abstract setting. You see this notion of dimension. Okay. So let me now just summarize this thing in a. But any question? Any question here? Yeah. So. I always use this vector notation when I'm talking about this explicit 2-dimensional or 3-dimensional examples. But when I talk about more general, I will always use the bracket notation. So if I give a set, say S is a vector space, okay, and so if you have some vectors, say V1, let's say A1, A2 up to an, some n vectors, then they all belong to S. Okay, and then consider equation alpha 1 A1 plus alpha 2 A2 all the way up to alpha n an equal to null vector. So we write down this. So consider the equation. There is this equation. Okay. So in this equation, I want to solve this equation for where unknown quantities are alpha 1, alpha 2, all these numbers, right? I want to solve that. So the statement is that if the only solution is all of them 0, alpha 1 equal to alpha 2 equal to alpha 3 equal to alpha n, all of them 0, okay, then this A1, A2, I mean this set of n vectors are linearly independent. Linearly independent. Okay, so that's a definition of linear independence. I mean, this solution will always exist, right? Because after all, if I multiply all of them by 0, each of them is null vector. The sum of the null vector is again null vector. So this will be always a solution. But the statement here is the important point is this one. If this is the only solution, there is no other solution. This is the only solution. Okay. So this is a thing. And the dimension, let me just come to the dimension here. So, what is the dimension? Dimension is the maximal number of linearly independent vectors. Okay. I'm assuming that this is finite. So assuming it is finite. So this is really I'm talking about for a finite dimensional vector spaces. In the infinite dimensional vector spaces, one has to be more careful. Okay. In the functions, when we talk about function spaces, one has to be a little bit more careful. One has to specify much more. But in this chapter, I'll be mainly talking about finite dimensional vector spaces. Okay. Most of the discussion will be for finite dimensional. So it's a maximal number of linearly independent vectors. Okay. So by that itself, I mean, it's very clear that is the good definition of dimension, right? Suppose in some example, this number is n. Okay. Suppose in some particular example, this maximal number of linearly independent vectors is n, and let's suppose those vectors are this. Okay. So we are saying this is the maximal number, right? What it means, if I take this set and put one more element, then it is no longer linearly independent, right? So if I take any other vector, okay, and put together, so now there are n plus 1. So since I'm saying that n is a maximal number, this n plus 1 guys cannot be linearly independent, right? Which means that if I consider this equation, alpha 1 v1 plus alpha 2 v2 plus alpha n vn plus, let's say, alpha v equal to 0 vector, if I consider this equation, then there exists a non-trivial solution. There exists, because they are not linearly independent. So there must exist, a non-trivial solution. When I say non-trivial, means not all 0. Trivial means when everything is 0. Non-trivial solution to this equation for alpha 1, alpha 2, right? Which means there exists a solution where not all of them are 0. Okay. Now let us see, is it possible that alpha could be 0 in this non-trivial solution? Could it be? So first question you can ask is that, so say I have found a non-trivial solution, which means not all of them are 0. Not all the alphas are 0. Now, in that non-trivial solution, could alpha have been 0? Alpha is this coefficient. Okay. Could alpha have been 0? Answer is no. Because if alpha was 0, then we are considering this equation, right? But we know that this vectors, v1 up to vn, that is linearly independent, right? Then the only solution would have been all these guys are 0, which means everything would be 0, right? You understand? So let's see. So the two possibilities. If alpha is 0 or alpha is not 0, two possibilities are there in this non-trivial solution, right? If alpha is 0, then if alpha is 0, this drops out from this equation, and then we are considering this is equal to 0, right? But I know v1, v2 up to vn is linearly independent, so the only solution would have been alpha 1, alpha 2 all the way up to alpha n is 0, right? So there is a contradiction. I mean, this would imply that all the alpha 1, alpha 2, everything is 0 due to linear independence of v1 up to vn of this n vectors is linearly independent by assumption, right? So this will be 0, and that would be a contradiction. That means this would be a trivial solution, right? So for any non-trivial solution, alpha has to be non-zero, right? And if alpha is not 0, then I can, you see, I can just take this on the other side, right? and divide by alpha. Since alpha is not 0, I can divide. That's the reason. I mean, you have to be sure when you divide by some number, you better make sure that that number is not 0. Otherwise, you will get infinite everything, right? So, yeah. So if you divide, so then I can take. So I can use this equation, take this on the other side. So you find our alpha v is equal to, or minus alpha v equal to alpha 1 v1 plus alpha 2 v2. Okay, and then I can divide by alpha, and that is where I'm using the fact that alpha is not 0 in the non-trivial solution. So then v is simply minus alpha 1 over alpha v1 minus alpha 2 over alpha v2, and all the way up to minus alpha n. I'll take out minus common factor. Minus 1 over alpha, let's take out. Then plus alpha n. Yeah? So you see that I have expressed v in terms of v1, linear combination of v1, v2, vn, right? That's why, I mean, so this you can think of as a basis vectors. Basis vectors is something such that any other vector can be expressed as linear combination of basis vectors. Okay. So therefore, you say the set v1, v2, vn form a basis vector set. Okay. So any vector can be expressed as linear combination of these n vectors here. Right. So indeed, you see that to specify any vector, I need to specify this n numbers. Right. So information I need to specify that any arbitrary vector is n. That's why its dimension is n. Okay. So this is the idea here. Any questions? This is a very important notion of linear independence and the basis vectors and so on, dimension of the vector space. Is this logic clear? I mean, this argument. Any questions on that? I mean, please feel free to ask anything. Any question? Okay, so this is a definition. So okay, maximum number. So and then okay. So the basis a maximal set of linearly independent vectors. Independent vectors. Okay. So basis is a maximal set of linearly independent vectors. It's a maximal set. So if I add any other vector to that, then it's not linearly independent. So I can express the new vector as a linear combination of the previous vectors. So this is the main idea here. Okay. But obviously, it's not unique, right? I mean, I said a maximal set, but there are many maximal sets you can put, right? In that example, which I erase now, you remember we had 3 vectors. I mean, we just consider 3 vectors. So in the example here, this was v1, this was v2, and something here, this was v3. See here. V3 with the components x1, y1. Okay, this was 1, 0. This was 0, 1. Okay. In this example, we said if I take v1, v2, v3, all 3 of them, they are not linearly independent, right? But if I take just V1 and V2, they are linearly independent. If I take V1 and V3, they are also linearly independent. So I could have chosen my basis as V1 and V2, or I could have chosen my basis as V1 and V3. It's equally, it's all right. There's no problem with that. Huh? So V1 and V2 could provide a basis. This could provide a basis. But equally well, I could have chosen V1 and V3. This could also have provided a basis. Or I could choose V2 and V3. They could also provide a basis. So it's not unique. There are infinite number of bases you can choose. Infinite number of basis vectors you can choose. Okay. So I mean, for example, let's say if I take an arbitrary vector V, which is say alpha beta. Okay, the two components are alpha and beta. Then if I choose this as my basis, I can write V as alpha V1 plus beta V2, right? That's clear, because V1 and V2 are that. But what if I choose V1 and V3 as my basis? So in that case, we want to find some, let's say, I want to solve the equation, say alpha prime V1 plus beta prime V3, that is equal to V. I want to solve for this equation, right? So to find what is alpha prime and beta prime. So let's write down, this guy is alpha prime 0. That is beta prime x1 plus beta prime, comma beta prime y1. That one. Because this is, I just multiply by beta prime, both sides, both components. And this should be equal to alpha beta. Right? So I want to solve for this. So let's solve this. So if I add them up, these two here, you find alpha prime plus beta prime x1, comma beta prime y1, that is equal to alpha beta. Okay. So now, so each component must be equal. You have this vector equality. So in particular, this must be equal to that. So that tells me that beta prime is equal to beta divided by y1. Remember, y1 is not 0. So I can divide. Okay. Now I plug that in the second equation. So you get here alpha prime plus beta x1 divided by y1, substituting that. That's equal to alpha. So this implies alpha prime is equal to alpha minus beta x1 divided by y1. So you see I found beta prime and alpha prime. That is what we were looking for. So see, V can be expressed as linear combination of V1 and V3, except the coefficients are more complicated. Here the coefficient was simply alpha and beta. Here the coefficient is beta prime is this here, and alpha prime is this here. It's more complicated, but nevertheless, okay, it's right. So there's nothing preferred about any particular basis vectors. Okay, there are infinite ways that you can choose the basis vectors. Of course, what makes it special, this V1 and V2, was because the inner product of these two was 0. They're perpendicular to each other. That is nice about it, right? But in order to talk about perpendicular or, I mean, orthogonal or not, you need to define what you mean by scalar product. But so far I have not defined scalar product, right? So this is without any scalar product. I have not defined scalar product yet. I mean, that will be next, in the next lecture. I will talk about scalar products. But okay, so let us see now what will happen if I change the basis. Say you choose one basis and I choose another basis. Okay, what happens when how can I relate the information I have to the information you have, right? That's a natural question you can ask. So let's do the following. I will now use some notation. Let me use the. I mean, in this notes for the basis vectors, there's a specific notation. Yeah, actually, the notation is simply this. So say say some n-dimensional space, n-dimensional vector space, and say there is a basis, let's say 1, I mean, there should be n, right? N vectors, the basis vectors. When you say dimension is n, the maximal set of linearly independent vectors is n, right? So the basis will always have n vectors. So you choose, I mean, I choose one basis, 1, 2, n. So this is one basis. Okay, but another basis, let's call it 1 prime, 2 prime, n prime. Okay, this is another basis. Okay, so say I'm given this basis. So in particular, I will just use this to instead of writing this n of these guys, I will just put here I. Okay, I goes from 1 up to n. That forms a basis. And here again, I will put here I prime, where I prime goes from 1 to n. So this is a basis vectors. Now, so any we said this is a basis vector. So any vector v, I can expand. Oh, sorry, I'm using not any vector v. I can expand as linear combination of these vectors. So let's say I will use the symbol here, vi I, summed over I. But I can equally well have expanded in terms of this second basis. Okay, coefficients will not be the same; they will be different, right? So if I expand in terms of the different bases, I will call them vi prime. There will be some different numbers, I prime. Okay. Now I want to ask, how can I? So you see that if I have chosen this basis, I will find these numbers for my vector. This will be components of the vector, right? In your basis, this will be different components. Now I want to ask, is there a relation between these two? How can I translate my results to your results? No? And that is obtained in the following way. Well, since this is a basis vector, so each of these vectors I can expand as linear combination of those vectors. Correct? Right? I mean, this is a basis, so I can expand this guy. I said this is a basis, so any vector can be expanded in terms of that. So simply, so take this, in particular this vector, this can be expanded as linear combination of that, right? So in general, I prime, where I goes from 1 to n, can be expanded, and let's say, I don't know if I'm using the same notation or not. I will write like this, ai, ij, j, okay, summed over j. So this can be expanded as linear combination of that, right? The coefficients I denote in this way. Why? You see, normally I would see when I expanded like this, I had just this coefficient vii, right? But here I have another. So in other words, jj, right? But this notation, this index I, is because I have also a free index here I, right? If I take, I mean, 1 prime and say 2 prime, etc., for each of them when I expand, these coefficients will be different. So to remember for which vector I'm expanding, I put this index I. Yeah. So if I expand like this, I will call this a1 j, sum j equal to 1 to n. Okay. For this one, it will be some different coefficients, so I just call them as a2 j equal to 1 to n, and so on. So just to, this index is just to remember which vector I'm expanding. Which of these guys I'm expanding, right? This will be different. The coefficients will be different for each of them. So to distinguish that, I put this index I. Okay, and this is just summed over. Is that clear? I mean, this point. Yeah. Now here, if you look at this guy, this I goes from 1 to n because this index I mean, there are n such vectors, right? And j also goes from 1 to n. So you can think of this as an n by n matrix, okay, where I say labels the row and j labels the column. Let me just write it like this. So you can think of this. So I goes from 1 to n, and j goes from 1 to n. So I can think of this as this all of this. There are how many? There are n square objects here, right? Because I goes from 1 to n, j goes from 1 to n. So there are n square objects. I can arrange them as an n by n matrix. Okay, So the matrix A, which will be denoted by A11, A12, A13, A1n, A21, A22, A2n, all the way up to AN1, AN2, ANN, right? So all these n square numbers I can arrange like this. So I refers to the row and J refers to the column. Okay, so there's a matrix here. Okay. So now, given this information, so what I've done, I have this basis, you have this another basis, and what I've done is I've expanded your basis vectors in terms of my basis vectors, and that defines to me this matrix A, right? Now, given this matrix A, I can immediately relate this and that, V prime to V. You see how I can do that? Can I erase this? I mean, this was just to show that this can be written as a matrix, right? Okay. So now let's just plug that in here. Here's I prime, so I can just plug this expression here, right? So what so the V is the same as V prime I prime summed over I equal to 1 to n. But now I use this thing, I prime is equal to that. So I'll find here V prime I, AI j, j equal to 1 to n. Right? Now relate that to this here. This is the same as Vj, j equal to 1 to n. You see, I should remember, I mean, maybe I'm not sure whether you're familiar. This index I is a dummy index. After all, I'm summing over I. So it doesn't matter whether I denote it by I, J, K, L, whatever symbol I need, I can use, no? Okay. So here I just use the J because here there is a J vector. So I just use the J here. Now you have an equation here. In fact, let me do the following. Let me take this and put it on the other side. Okay. So this equation implies that Vj minus sum I V prime I Aij, this whole thing multiplying j summed over j equal to 1 to n is equal to 0, is equal to null vector. Correct? All I've done is I've taken this on the other side, this side here. I mean, we have this is equal to that, right? I take this on the other side, right? So this minus that should be the null vector. If these two vectors are equal, this minus that must be equal to null vector. That's what I've done here. But then furthermore, I've used the distributive property of with respect to addition of numbers, right? You see, I've taken j as the common. Take the jth element and combine and put the two coefficients together. That's all I've done. I mean, I've done two steps in one stroke. I hope there is is that clear, or should I do step by step?
Just step by step.
Okay. So there's of course I equal to 1 to n. This is a mistake. I mean, here this summation is always there, I equal to 1 to n. Then what I did, I prime is replaced by this, right? So this involves a sum j. So there is a sum j equal to 1 to n and sum I equal to. So there is that, and then V prime I AI j. Correct? Now notice that here I exchange the sums. You see, look at this here. There is a summation over I here, but this I prime itself involves a summation over j. So I put here like this. But in writing that, I have conveniently exchanged the limits, exchanged the sums. But there is no problem here. This exchanging the sums is commutes. I mean, it doesn't matter whether first you sum over j or first you sum over I. Okay. This is true in finite dimensional cases. In infinite dimensional cases, there could be some subtlety. Okay. So there you have to be careful. But I'm here talking about finite dimensional cases. In finite dimensional cases, it's always you can exchange, right? Yeah. So this is I did, and that is equal to null vector. That's what we are saying, right? Because since these two are equal, so difference between these two must be null vector. Okay. Now what I'm doing, I'm taking the say jth vector here and putting its coefficient together. Okay. So take the j as a common factor, let's say. So when I take the j as a common factor, j equal to 1 to n, there is this summation is also common. So I put everything outside, right? And then here you have vj, and here you have minus sum I equal to 1 to n, v prime I, aij. This whole thing is multiplying j, and that's equal to null vector, right? So that's what I did. I did two steps there in one stroke. Okay. Now, so what does that equation imply? You see, the set this vectors j were a basis. They were linearly independent. So such an equation will have only trivial solutions. These coefficients must all be 0, right? Because j are linearly independent. So this implies that since the set j with j equal to 1 to n is linearly independent, then therefore this implies that each of these coefficient must be 0, which means that vj must be equal to sum v prime I aij. Okay. So you see, I have related those two coefficients. V's were the coordinates the coefficients I was finding in my basis. V primes were the ones you are finding in your basis. And now I have found the relation between these two once I specify this matrix A. Okay. That's the idea here. There's a relation. I mean, you can go from one basis to another basis. Now, okay. So in terms of the matrix notation, I can write it in the following way. If you think of in fact, maybe I should not. Let me try to use the same thing. I mean, it's a matter of which one I call row, which one I call column. It doesn't matter. You see, I was calling this as a row and that as a column, but I could have done other way around. That is just to write in the matrix notation. Let me try to see what is used here in this notes. 10 as far. Special properties, change of basis. Where is the change of basis? I'm not following the same sequence as these notes. Yeah, change of basis. Let me see what is the. R inverse A. I don't remember what they're using. I mean, anyway, at this stage it doesn't matter, whichever you call. I mean, if I call this as a row and that as a column, so I can think of V as a row matrix. You see, V1, V2, Vn. This is, I think of, put these n numbers in a row. Huh? Okay. Similarly, V prime, you put it in a row. V prime 1, V prime 2, V prime n. Okay. Do that. Then you can write this equation in the matrix equation, V equal to V prime times A as a matrix multiplication now. So you take this row and multiply to this n by n matrix with the usual matrix multiplication rule. You know how the matrix multiplication rules are. You take the row of the first matrix and multiply it to the column. No? So, okay. So this is just using matrix multiplication rule. So you can, yeah, instead of writing all this long expression in terms of sums and so on, you can write very conveniently as a matrix equation. Okay. That is if you so here if I think of I as labeling row and J as labeling the column. Okay. But if I think of I as being labeling column and J labeling row, then I would think of these guys as column vectors. Okay. And then the equation will become V equal to A times V prime. Okay. Now I don't remember in this notes which convention they are following. Okay. We'll come to that. I mean, when I go, I don't remember now what convention they were using here. Okay. Anyway, it doesn't matter. It's a matter of convention. It's nothing more than that. Essential point here is that the two coefficients are related to each other by this matrix A. Right? So let me just state it. If I think of this, this is in this language where I think of this as a row and that as a column. If I think of this as a column and that is a row, then the equation would be V equal to A V prime, where V and V prime are column vectors, are column matrices instead of row. This is row matrix, right? There it will be column. If I think of, so here in this equation, I'm thinking of I labeling the column and J labeling the row. Okay, it's a matter of convention. You choose some convention, then you can write down matrix equation. But the important point is that they are related. Okay. Now another thing. You see, I mean, could this matrix be anything? I mean, one could ask, could this matrix be anything? You know, I mean, is there any condition on this matrix? No. There is one condition, and that is the statement that this matrix is a non-singular matrix. Okay. So in other words, so let's see. So we said, see, both I prime and J are bases. Here what I did was I expanded I prime in terms of J, but I could have done other way around. I could have expanded this J vectors in terms of I prime, right? So I could have expanded, since I prime, all the I prime vectors with I going from 1 to n is a basis. I could expand the vector J as a linear combination. Let's call it A prime J I prime. Okay, I could expand. I mean, because I'm just using the fact that this is a basis. Not, let me call it K here. K. K is summed over, right? K equal to 1 to n. Okay. I mean, this is true because simply it's a basis. I primes are basis. Now let's plug that in here. Okay. I mean, now say on this side J, I plug this expression for J. Then that implies I can erase this part now. So plugging this in here, you find I prime is equal to summed Aij, j equal to 1 to n, and then I write for j that expression, which is sum k equal to 1 to n a prime k j k prime. Okay. So this is the same. Actually, I could write it in the matrix notation, right? So you have Aij. So think of this as the row that is the column. This is the row that's the column, right? Then this is nothing else but A times A prime, as in the matrix language. This whole thing, it's index. I'm taking the ith row and kth column, right? This multiplying k prime summed over k equal to 1 to n. But now again, take it on the other side. Okay. And let me write also I prime. Okay, let's look at the, so I prime minus sum over k equal to 1 to n a dot a prime, a times a prime, the matrix language, matrix multiplication, k prime, that's equal to null vector. I took this on the other side, you get a null vector. But now these are linearly independent. I mean, this prime, all these I primes are linearly independent. That means that in this sum, okay, so let's see. Suppose I take I prime equal to 1. So what do we get? 1 prime minus summed k equal to 1 to n a dot a prime 1 k prime, right? This is true for each of them. So for 1 prime, similarly there will be another equation for 2 prime and so on and so forth. There are n equations here because I is a free index. This is true for every I. So there are n equations. So if you look at the first equation, this is suppose this is equal to null vector. So you see, because they are linearly independent, whenever k is 2, 3, 4, 5, etc., then this must be 0, right? And when k is equal to 1, this must be, so a times a prime 1, 1 must be equal to exactly 1 to cancel that, right? So what we are seeing, the conclusion from this is that so a times a prime 1 k equal to 0 when k is not equal to 1, right? So when k is equal to 2, 3, etc., this must be 0 because here there is only 1 prime, right? And a times a prime 1, 1 must be equal to 1, right? I mean, again, I'm using just the linear independence of that, right? Is that clear? I mean, just write this equation. This equation is 1 prime minus a times a prime 1, 1, 1 prime minus a times a prime 1, 2, 2 prime, and so on, minus a times a prime 1 n prime. That's equal to null vector, right? I just open this up. I just explicitly write sum over k, right? K equal to 1, 2, 3, etc. So like that. Now this is a linear independent. That means coefficient of each of these must be 0. Each of these linear, I mean, only solution is put these two things together, right? Because 1 prime is a common factor. So that's the same as 1 minus that, right? So they are linearly independent. So each of these coefficients must be 0. So that's what I did here. So a prime 1k for k equal to 2, 3 all the way up to n is 0, whereas a times a prime 1, 1, that must be equal to 1 to make this coefficient 0. Now you do the same thing for 2, 3, etc. If it is 2, what will happen? Then the equation is, when I is equal to 2 in this equation, you get that, right? And now you see that this coefficient will be 0 whenever k is not equal to 2, right? And when k is equal to 2, this must be equal to 1, right? So another equation you find is a times a prime 2k equal to 0 when k is not equal to 2, and a times a prime 2 is 1, right? Do that for everything, for each of them. You see, already you can see from this equation you see for arbitrary I, when k is not equal to I, this must be 0, this coefficient must be 0, and when k is equal to I, it must be equal to 1, right? So the general formula that we are obtaining is this here: a times a prime I k equal to 0 whenever I is not equal to k, and a times a prime I k equal to 1 when I is equal to k. That is the unit matrix, right? The identity matrix, right? All the off diagonal terms are 0 and all the diagonal terms are 1, right? So we are concluding that a times a prime is identity matrix, right? which means A prime is the inverse of A. Okay. So the conclusion from, so you can summarize as a matrix equation now. A times A prime is equal to identity matrix. I'll put here, I use this kind of block 1 to indicate that this is a matrix. This is the n cross n matrix. Identity of the n cross n matrix, which is nothing else but 1, 1, everything diagonal 1 and everything else 0. That's this matrix. Which implies A prime is equal to the inverse of the matrix, inverse in the matrix sense. Okay. Okay. So that's a very important point here. So what we are saying is that this matrix is not arbitrary matrix, the matrix which links the two, which relates the two bases. It must have an inverse. There must be an inverse existing for that matrix. See, for general n by n matrix, inverse may not exist, right? So it's not a completely general arbitrary matrix. It's a matrix whose inverse exists. Okay? And do you know when a matrix inverse exists? What is the condition? Precisely. Its determinant must not be 0, right? So A is a matrix whose determinant is not 0. Okay? So that's what is called non-singular matrix. When the determinant is 0, you say it's a singular matrix. Its inverse does not exist then. So this is the important point. But that's all. That's the only condition for the A. The determinant is not 0. That's the only condition. So there are infinite number of ways you can choose a basis, because take 2 by 2. 2 by 2 matrix, if it's suppose it's two-dimensional space. Okay. Sorry, its time is 11. No, but we started much later. Yeah, okay, I will finish in 2 minutes. Just given one example. And, 2 minutes, I'll stop. Okay, so if I take 2 by 2 matrix, say n equal to 2. 2 by 2 matrix, suppose A will have, it's a 2 by 2 matrix, so there will be some A, B, C, D, four numbers here, right? And we have one condition. What is determinant of A? Determinant of A is the product AD minus BC, right? So all we are saying is this is not equal to 0, right? But still, you can, subject to this condition, you can choose any value of A, B, C, D. So there are infinite ways of you can choose the different bases. For every such choice of A, B, C, D, this will give you a different basis, because, right? After all, what was the A? It was the V. V is equal to what did I do? V prime. V. I don't remember what was the equation I wrote. I erased it. V equal to A V prime or V prime A, something like that. Depending on which way you choose. But anyway, so you see, for each choice of A, I find a different basis here. So there are infinite ways of choosing the basis. Just as a side comment, I should say that if you consider the set of all matrices, okay, all matrices whose determinant is not equal to 0, okay, this set forms a group. You don't know what is a group, but in some sense you can think of the following way. So I start from one basis. I apply A, some matrix A, I get a different basis. Okay. Then I apply another matrix, let's say B, on that, I find another basis, right? So first I apply this V equal to V prime A, and then on V prime I again apply another matrix B. So I'll write here. So this I write V double prime BA. So V prime is V double prime B. Okay. So you see that B times A now. Let's think of this. This is another matrix, n by n matrix. Okay. This is transforming V to V double prime. Right. So the successive transformations will be a valid transformation in the sense, indeed it's clear. What was the condition? Determinant of A must not be 0. Determinant of B must not be 0, right? But then it's automatically guaranteed the determinant of B times A is also not 0, because the determinant of the product is the same as product of determinants. Remember this equation. If you don't, I mean, I will probably review some of these things. Determinant of B times A is the same as determinant of B times determinant of A. So if neither of them is 0, then obviously this is also not 0, right? So this forms a group. Actually, the set of all such matrices whose determinant is not equal to 0 forms a group. I'm not defining precisely what I mean by group here, but it's a set of all possible transformations of basis. All possible transformations of the basis forms a group. This is a special example. Okay, I think I'll stop here. And so next Wednesday, I will just introduce the concept of inner product, scalar product, the length, the notion of length, and start talking about, there's a dual vector spaces. You might have seen in the, I mean, for such vectors, there's also the other one, right? You have J, in quantum mechanics, you have seen this notation. These are the dual vector spaces, dual vectors. So we'll discuss that, and then talk about the linear operators. We'll start discussion of all this. Okay. Okay. Any questions? Okay. So maybe you should get some lunch. Yeah.